Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. I bid to the panels. I am Muhammad Huzaifah bin Yaacob, a student from Bachelor of Science on Applied Chemistry, and I am doing my final project entitled Behaviour of N-dimethylaminobenzonitrile, DMABN in molecular solvents and deep eutectic solvents, and I have been supervised by CHM Dr. Muhammad Azizi Nawawi. Molecular solvents are those chemical compounds that have carbon-based molecular structures typically used in research and development industries. But they have disadvantages, which are toxicity, high volatility, high polarity, and linked to the health difficulties. For example, water and organic solvents. But now researchers find green solvents, which are environmentally friendly solvents or biosolvents, which are derived from the crops, as they compromise good properties such as low volatility, non-toxic, and biodegradable, non-hazardous, but it has relatively high in viscosity. For example, of green solvents are deep eutectic solvents and ionic liquid and supercritical fluid. In this study, I use molecular solvents and deep eutectic solvent as the solvents. The eutectic solvents are ionic liquids formed by combining two or more components at a specific ratios by combining a hydrogen bond donor HBD and hydrogen bond acceptor HBA. The common HBA in industry are choline-chloride, chlorochlorine-chloride, and acetylchlorine-chloride. Meanwhile, the famous HBD are malonic acid, glycerol, urea, and ethylene glycol. The figures below is the schematic representation of eutectic point on HBD and HBA when they mix, and we will get the low melting point. As we know, the common molecular solvents in industries leads to the various environmental problems and challenges due to their toxicity, high polarity, and high volatility. But then the researchers found green solvents, which are DES and ILs, for alternative to these molecular solvents. But then these type of green solvents are not widely applied in this industry due to their high viscosity.
Hence, in this study, fluorescent molecular rotors (FMRs) are introduced and used as probes in sensing polarity and viscosities behavior in molecular solvents and deep eutectic solvents. And it is to understand the viscosity and polarity at a molecular levels, which differs from the machine measurements. And the applications of FMR usually used in biological cells, polymerization, oil, and fluids.
The objectives of these studies are to synthesize a series of the eutectic solvent with different viscosity and polarity, to characterize the physical and chemical properties of the eutectic solvents, and to correlate fluorescent emission intensity of the MABN to the polarity and viscosity of the eutectic solvent and molecular solvent using the Foster-Hoffman equation. Now we move to the literature review. For the first part is fluorescent molecular rotors, FMRs. FMRs are organic molecules that have a rotor moiety which allows them to revolve freely in the solutions, as they can affect the fluorescent emission properties by changing their environment such as polarity, viscosity, and refractive index. Due to their unique structures that can exhibit intramolecular rotation, they can absorb and emit light such as excitation and emissions, and they can useful in chemical sensing, biological imaging, and nanotechnology.
The second part is the DMABN as a prop. Figure 1 shows the DMABN structures by Shiba et al. 2007. It is a yellow to brownish solid crystal which has a molecular weight 146.19 gram per mole and stable under the normal conditions. Figure 2 shows the rotor arm of the dimethylamino group functions with the benzene rings, and the cyano group provide rigidity for the control rotation. For figure 3 shows the photoexcited DMABN undergoes charge transfer from dimethylamino to benzonitrile moiety, and this rotation can be achieved by photoisomerization, which is the molecule absorb the photon with the right energy, which result in rotation around the central axis, and the rotation can be investigated by fluorescent spectroscopy and nuclear magnetic resonance spectroscopy.
Now we move to the methodology part. The first part is synthesize a series of DES with different polarity and viscosity. The first samples of DES are choline-chloride urea, choline-chloride ethylene glycol, choline-chloride glycerol, and choline-chloride malonic acids were used in the study. As the steps to synthesize a series of DES are different mole ratio of HBA and HBD were mixed, and the mixture were ground using a pestle and mortar, and the mixture were heated at 60 degrees Celsius for 2 until 4 hours until the colorless solution formed. And the solution was dried in a vacuum drying at 50 degrees Celsius for with pressure 10 MPa for 8 hours, and then the solution will cool in the desiccator for further use. FTIR and LMR spectroscopy were used in DES characterization. The FTIR branch is infrared 35 per kin element spectrophotometer with the scan wavelength 650 until 4000 cm -1, with the scan number 4 cm -1 and scan resolution 8 centimeter -1. For the NMR brand is Bruker Advanced 400 spectrometer with the 16 scans for 1H and frequency 500 MHz. And the ES samples were dissolved in deuterium oxide solvents. This is the methodology of UVVs and fluorescent measurements. As to make a stock solution, the DMABN crystals were dissolved in methanol, and the dye stock solution was spiked in molecular solvents and deep utility solvents and mixed with the water mixings. And for the UVVs measurement, the absorption was done by lambda 35 per kin Elmer UVV spectrophotometer with the scan wavelength 190 until 600 centimeters -1, and the lambda absorption of molecular solvent and Eutectic solvent was determined and recorded from the spectra. And for the fluorescent measurement, the scan wavelength is from 200 until 600 centimeters -1, and the slit setting is 15 nanometer for both excitation and emission, and the emission wavelength is 310 nanometer with excitation wavelength 295 nanometers, and the emission and excitation spectra were recorded. And to correlate fluorescent emission intensity with solvent viscosity, we plot the graph log intensity versus log viscosity using Foster-Hoffman equation. This is the FTIR measurements of the ES for choline-chloride urea and choline-chloride malonic acid. As can be interpreted from the graph and tables, the wave number of the ES shown as similar to the functional groups of HBA and HBD respectively.
This is the results of FTIR spectroscopy of choline chloride, ethylene glycol, and choline chloride glycerol. The similarity between glycerol and ethylene glycol molecules causes the appearance of the same vibrational bands in the DS choline chloride, ethylene glycol, and choline chloride glycerol. This is the NMR spectroscopy of one hydrogen. The spectroscopy was done to further confirmation to the DES structures. As can be interpreted, some of the peaks were shown and some of the peaks were overlapped with each other. And due to this, the different functional groups can lead to the different chemical shift, and the peak splitting helps in determining the numbers of neighbors protons.
This is UVV's absorption spectra of the DMABN in molecular polar and non-polar solvents. As can be seen, there is two absorption peaks in polar solvent corresponding to the locally excitation, Le, and charge transfer CT, but only one absorption peak shown in non-polar solvents corresponding to the CT peaks. And it can be noted that wavelength absorption peak CT in polar solvent are consistent in terms of viscosity, and the non-polar solvent have weaker interaction with the polar groups of the MABN. From previous literature review, there is no specific dielectric constant of DES, as dielectric constants means their polarity. But due to DES absorption peaks similar with the polar solvents, which have Le and Ct absorption peaks, it might be concluded that these DES are polar solvents. Hence, the wavelength absorption Ct in DES are consistent in terms of viscosity. This is fluorescent emission spectra of the DMABN in solvents at wavelength excitation to 195 nanometer. The DMABN emits higher emission intensity in non-polar solvents, meanwhile redshifted emission occur in polar solvents. The plotted graph correlation of log intensity versus log viscosity in polar and non-polar solvents shows the intercept lines are non-perfectly linear. The lower R squared means the viscosity of the solvent did not influence it much by emission intensity. And this is fluorescent emission spectra of the MABN in deep utility solvents at wavelength excitation to 195 nanometer. The MABN emits an increasing of fluorescent emission intensity as the deep utility solvent's viscosity increase. The plotted graph correlation in deep utility solvent show the both intercept lines for Le and Ct emission peaks are non-perfectly linear, as the log intensity increased by increasing the log viscosity. And I can conclude that the low R squared value for Le and Ct emission intensity did not influence so much on the viscosity.
In conclusion, the MBN has exhibited a complete dependency of emission intensity on both solvent polarity and viscosity. Hence, it is challenging to separate the effects of viscosity and polarity influences of the MBN in molecular solvent and lipid solvent, as the MBN is probably more sensitive to the polarity than viscosity, as can be seen from the absorption, emission intensity, and the correlation graph. Hence, all the three objectives were achieved as to synthesize and characterize lipid solvent and to correlate the emission intensity with viscosity. As recommendation for the better understanding, we can try other fluorescent methods such as fluorescent quantum yield and fluorescent lifetime. Other than that, we can measure the actual polarity index of the eutectic solvent by using an optical goniometer. Last but not least, we can try or change to the other fluorescent molecular rotors, as different degree of fluorescent molecular rotors will show different polarity and viscosity behavior. So that's all. Thank you.